It is section 7.2, exponential change and separable differential equations. In many real-world situations, the rate of change of a quantity y is proportional to its size. Such a relation can be written as in this equation by using a constant k. Such quantities are said to undergo exponential change. We'll deal with three different kind of examples in this section. First, we'll try to solve this differential equation. In the first step, we divide the equation by y, then we can get this equation. Now we integrate both sides with respect to t. Then here for left hand side, we can get that is now logarithm and the absolute value of y, and we consider this y as a function of t. And this is constant, so that there's kt and plus c. After taking the exponential function, we reach that. And now here, and eliminating the absolute sign that we put here, plus or minus, and then we can separate these two, and e to the c times e to the kt. We define this term as a variable a, so that we reach at y equal a constant, times e to the kt. Okay, and if we have initial value, and when t equals 0, our value is now, the value is y0, then from this one here, y0 at 0 is same as a times e to the now kt, which is 0, so that is a, but a we already from the data is y0, so the a0 will be replaced by y0. So we have this solution. That is the solution of this initial value problem. Okay, here now when we try to solve this equation, we were at this position. Now this can be, this red portion can be changed in this way. Now here is a kind of a chain rule we are using, but here, so that we already know that here y prime over y integration is same as logarithm of y. We used this knowledge and here, but now rather than that, if we write down for this portion to be here dy, then from this one immediately we can get again there's a logarithm of y absolute value. So that now we may consider that left hand side rather than dy over dt, dy over dt and dt, just simply that is just a dy. So that is integration of 1 over y with respect to y, right? So here, from that equation, we try to separate out, and dt will go right side, and y and 1 over y in the left hand side. Then now we reach that one, and then from this one here we can get integration here 1 over y and dy equal integral of k and dt. That integration is with respect to t, that integration is with respect to y. After separation, everything over there is including y variable only. The right hand side, it is only a function of t, then we can integrate separately. That's a technique. Okay, we'll explore this technique for later examples. Okay, here we have separable differential equations. In general, first order differential equations are given in this way. dy over dx is a function of xy. And of course, f of xy is a sort of slope because dy over dx is slope. But usually it is a general function of x and y. But once f is given in this way, and g of x times h of y, so they are separable as a function of x and as a function of y, then we say that the differential equation is separable. The slope is separable, then we say the equation is separable. And in this case, it's quite easy to handle. Here, y variables move to left-hand side, so divide by here h of y, and now multiply dx, then we can reach at that one. And then we apply integration. Of course, here left-hand side, integration is with respect to y, and right-hand side, integration is with respect to x, as we did earlier here. Okay, now let's try to solve this differential equation. Okay, for that one, now that is separable. Everything is along with multiplication so that it is separable. Now we keep y terms on the left-hand side and x terms to the right side. And first we divide by that one, and then multiply dx. Then, okay, and divide by also, x plus 1. Okay, then left-hand side will be y over y squared plus 1 and dy. Okay, everything, we consider this term, that one, and this one. Now, everything else must equal the other side. Okay, so it's x over x plus 1 dx. So from this one, now integration of y squared plus 1 on the bottom and top y dy equal here integration x over x plus 1 dx. So after evaluating these integrals, we can get the answer. Okay, and for left-hand side, it's quite simple. If you consider this as f of y, then it's a constant multiple of f prime y. Right? Here, that is, in fact, now, so that we can get that is half of, and if you multiply 2, then it's now derivative of that, and 1/2 you can put over there. So that is same as half and logarithm and y squared plus 1, and that's done for the left-hand side. How about the right side? Okay, let's try to here manipulate this integrand x over x plus 1. That is same as x plus 1 minus 1 divided by x plus 1, which is same as 1 minus 1 over x plus 1. So its antiderivative must be x minus, and from this one we have logarithm of x plus 1 and plus c, right? That is now the integration. You may stop here. It is a function is implicitly defined, so that you may stop here. So that's the answer. Okay. Okay, now we'll consider examples, and 3 examples. Here, the first one is population growth. When the number of individuals in population is large, then the population can be approximated by a continuous function. And also, we may assume that the function is not differentiable, and so that we can use a calculus technique to model and to solve the problem. Okay, here, for modeling, we need some assumptions. And here now, the proportion of reproducing individuals remains constant, and also assume a constant fertility. Then, at any time t, the birth rate is proportional to the number of individuals. So that's the assumption. And also, we assume that the death rate of the population is now stable and constant. And of course, that is proportional to the y of t. And also, and final assumption is that the departures and arrivals are negligible. Then here, the growth rate dy over dt is the birth rate minus the death rate. So that here now, dy over dt is same as b minus t, birth rate, and that is death rate, and y. So we may say that is k, so that this population growth can be modeled into this simple equation. Already we know that here now the solution is now y0 and e to the kt. We already know that, right? Okay, let's try to solve this example. The biomass of yeast culture in an experiment is initially 29 grams. Start with 29. So that one means that this is now y0 is 29. After 30 minutes, the mass is now 37. When t is 30, the y value becomes 37. Assuming that the equation for unlimited population growth gives a good model for the growth of the yeast when the mass is below 100 grams, which means that now the model can be expressed by that equation, and so that the solution is in this form. How long will it take how long will it take? Okay, that's typo. Take for the mass to double from its original value. Okay. So we may begin with the solution, y equal y0 and e to the kt. The first line is saying that it's 29, and that second line is data. Okay, let's try to use that one. After 30 minutes, the mass is 37 grams. Okay, the solution is now y equal 29 and here e to the kt. We have to decide k. So possibly this second line is for k. We can use that. And 30 minutes later, it becomes now 37. So that 37 equal 29 e to the now k, and that is 30 minutes, right? So that from this one, here 37 over 29 equal e to the k 30. Now from this one, if we apply logarithm both sides, then that one will become k times 30 equals now natural logarithm of 37 over 29. Okay, so here we have k is same as 1 over 30, and then natural logarithm of 37 over 29. Okay, we found the k. Now, how long will it take for the mass to double, which means that initially 29, it becomes 58, so that 58 equal 29 e to the kt. So divided by 29, it becomes 2, so that from this one, e to the kt equal 2. Now we are applying logarithm, then kt equal logarithm 2, so that we have to find the t, time, which is same as now logarithm of 2 divided by k. But k is known here already, so that plugging this one 2 over there, now I earlier computed, it becomes 85.38 approximately, so that we can find the time t. 85 minutes later, it becomes now double. Okay, so here in such a problem, some data will be given. That line here, we used it for finding k. So in this model, k and t and y0, everything must be given. Out of these three, here, now at least 2 must be given to decide the other, right? So that is used for determining k. Okay, let's see later on, the problems will be given in this way. The second example is radioactivity. Some atoms are unstable and can emit mass or radiation. Such a process is called radioactive decay. Now, from experiments, we know that it's quite well approximated by such a model. And that means that the decay, rate of the decay is proportional to the quantity. Okay, so we can write in this model. Of course, here we can solve it this way, so that radioactive decay can be modeled in this way. Okay, here half-life. Half-life is the time expected to become half of original quantity. So now for that one, here start with y0 and it becomes half y0. Then here from this one, here we can solve the problem quite easily. Assume we know k, we can decide the time. So from this one, now y0 can be cancelled and now apply a logarithm. Then minus kt is same as now logarithm of a half. This minus, so that now kt equal now logarithm 2 divided by k, we reach at here half-life. Okay, from this one you can get here now that quantity. If we know k, then we can decide half-life. Okay, the half-life of plutonium isotope is 24,360 years. If 10 grams of plutonium is released into the atmosphere by a nuclear accident, how many years will take it? How many years will it take for 80% of the isotope to decay? So the remaining part is only 20 percent. Okay, now we'll try to here use the information to decide K and time. So right now the question is about time, and for the isotope become 20%. But first we have to decide K. Now that one here, first line is saying about half-life. We are using that here equation to find the K. So K must be same as here logarithm 2 over now half-life. So that is same as a logarithm 2 over here 24,360. Right? That's the K. Now, and that will give you K. K is now decided. But the answer is here y equal y0. In the beginning, that is 10 and e to the minus kt. That's the solution of the radioactive decay, right? And already we know K. Now, and here 80% of the isotope is decayed, which means that remained is 2. So here we have to find T such that, okay, the unknown is T, it will satisfy this one, 2 equal 10 e to the minus kt. Okay, so that is now 1 over 5 and equal e to the minus kt. So from here now, okay, taking logarithm and multiply minus 1, so we get here kt equal logarithm 5. And we have to find the t. T is the known, so that divide by k. So here the time t equal 1 over k times logarithm of 5. Now already we know k is given this way, so that here use this one, then we can recheck that term, and if you try to find the numeric value for that, then it is 56,562 approximately. Okay. In that way, you can solve the problem. Here, the first line is used for the determination of K. Okay. Okay, now that is the third and last example, heat transfer, Newton's law of cooling. The rate of heat exchange between an object and its surroundings is proportional to the difference in temperature between the object and the surroundings. That is the Newton's law of cooling here. And we can do in modeling here, H is the temperature of the object, and Hs is the surrounding temperature. Then now rate of change of the temperature is proportional to the temperature difference and object temperature minus the surrounding temperature. So we can start with that one. If we solve that, then it's separable, and H terms on the left-hand side and T terms on the right side. And here, the same way, we try to get, after integration, we can get that one. And again, now we apply exponential function, and here we recheck that model. So that is the solution. Okay, there's a solution for the heat transfer. Okay. Now let's try to solve this example. Hard-boiled egg at 98 degrees Celsius is put in a sink of 18 degrees Celsius water. And after 5 minutes, the egg's temperature is now 38. Okay, that is initial temperature 98. And then when T is 5, the egg's temperature becomes 38. Okay, this is data information. Assuming that the water has not warmed appreciably, that means considerably. So that means the water temperature, the surrounding temperature is not changing by an observable amount. How much longer will it take the egg to reach 20 degrees Celsius? Okay. So here, now the surrounding temperature is 18. So by following this solution is 18 plus, now H0 minus HS, 98 minus here 18, and e to the minus kt, so that the solution is given in this way. Okay, now we'll try to use information. The second line is saying that after 5 minutes, the egg's temperature becomes 38. That means that now it becomes 38 and 18 plus 80 and e to the minus k when t is 5. Right? Okay, if we move this one to the left-hand side, that'll be 20 divided by 80, so that 1/4 will be now e to the minus k5. Right? Okay, we are taking logarithm and then multiply minus, then that is now 5k. Okay, from this one, 5k becomes logarithm of 4. So that from this one, k is now logarithm 4 divided by 5. Okay, this second line is given to determine k. Now, here, we have to find the time. So here the question is, we have to find the time, but how much longer than after 5 minutes, we have to measure the later time. But anyway, we try to find the total time, and then we try to subtract 5. So we have to decide the time so that the egg temperature becomes 20. So that is now here 20 equal 18 plus 80 e to the minus kt. K is already decided so that we can decide the time. That is 2. So that here 1/40 divided by 80, we reach that one, e to the minus kt. So that here, taking logarithm and multiplying minus 1, we get here kt equal logarithm 40. Okay? So here time is the same as logarithm 40 divided by k. So we are using this quantity, then that is same as here now. Okay, so that is k. 1/k is now logarithm 4, and that is 5. That's now logarithm 40. Right? So here you see that 5 is changed into 0.2 on the bottom. So if you compute this one and try to find the numeric value, then it's about 13. So here, that is about 13. So that, and after 5 minutes, the total time is 13. So that, and after that, and another 8 minutes later, it becomes 20 degrees Celsius. So the answer must be 8. Okay? Okay, that's the end of the section. Thank you.